Hi ladies and gentlemen, this is just a quick video to look through at variation of parameters. A really important idea that is not necessarily explained that well in a lot of textbooks. Let's just jump right in. So what we have with variation of parameters, we're looking at, in this simple case, a second order ODE with constant coefficients. I will tell you that this idea actually applies even when we have non-constant coefficients, but I'm only talking about the constant coefficient case in this situation because it's really easy for us to find the two solutions that go into solving the homogeneous equation. And so that's where we start. Always, our first step is we're going to solve the associated homogeneous equation. Every non-homogeneous ODE has one of these, and we solve, and in general, we're going to find the complementary solution as long as we can create two linearly independent solutions. So we have our complementary solution here. Sub H, of course, means homogeneous. And now what we're going to do is we're going to create a general solution. The general solution is the sum of our complementary solution along with a particular solution. And really what we need to do is come up with a way of finding a particular solution. So this is actually taken from Peter V. O'Neill's textbook on advanced engineering mathematics. I've made some modifications to it, but it's his section 2.3.1 variation of parameters where I've added in some content. So the bottom line is actually pretty straightforward. We have the complementary solution, which is a linear combination of the two solutions that we found to our second order ODE. And what we're going to do is follow exactly the same idea. However, we're going to replace the constant c with functions. And this is where the method gets its name, variation of parameters. We're going to allow the parameters to vary. Then we have a solution, at least we think we do. And anytime we think we have a solution, we're just going to substitute it back into the differential equation. And we'll, of course, need to calculate a couple of derivatives. Through this process, then, the first derivative, which leverages the product rule a couple of times, we're going to end up with what we see here. Quite straightforward. However, at this point, we are going to apply a condition. So we have two unknowns, a1 of x and a2 of x, and we need to have two conditions. This is the opportune and not necessarily obvious place that we're going to apply one of those conditions. One of the conditions that we're going to apply is right here. We're going to take this piece of the derivative and we're going to set it equal to 0. That's what this is doing right here. And the reason we're doing that is actually pretty straightforward. We want to avoid having second derivatives for our unknowns. And so we're just going to extract those by applying this condition. And what's left then is shown right here. We have a simplified version of the first derivative once we've applied this condition. Now what we're going to do is, of course, find the second derivative. Again, product rule. And when we apply the second derivative, we're going to end up with this item here. Now we have the first and second derivatives. We're going to plug these back into our differential equation. And we can see clearly this piece here is yp double prime, and then we have plus, and we have a p here, and then this piece is y prime. And then we have plus q times, and this last piece is y. And of course, these are all the particular solution pieces, and this is f of x. And now what we have is a little bit of algebra to rearrange these terms and make it look like this right here. And then it's at this moment that we see the payoff for the way in which the variation of parameters is actually working out. Because we have guessed our particular solution based upon the solutions that build the complementary solution, the y1 and y2, we can see the following. This item here and this item here are actually nothing more than the application of our solutions to the homogeneous equation. And what we see is these are both 0. And what that leaves us with then is our second constraint, which is just this piece here. And so moving through, we see that is our set of two constraints. What we need to find then is we have the unknowns, which are a1 and a2, and in this case we have the derivatives for each of those. We have a1 prime and a2 prime. So we're going to set up this system of equations in matrix form right here in order to solve for a1 prime and a2 prime. So it turns out that quite frequently in differential equations we end up seeing this matrix right here. It's called the fundamental matrix. And I've highlighted that for you right here. This is a new vocabulary term, but this comes up all the time. And when we substitute the fundamental matrix in here, it's not really a substitution, we're just recognizing what it is. We're replacing the matrix out in front here with what it's actually called, which is the fundamental matrix. And I've reintroduced the X notation now because we're going to start solving, and eventually we're going to solve once we find a1 prime and a2 prime for a1 and a2. So it turns out that if we take a look at the determinant of our fundamental matrix here, then we're looking at the determinant of this item here, and we find the determinant of a 2 by 2 matrix is just the Wronskian. So the Wronskian, named after Polish mathematician Wronski, is nothing more than looking at this determinant for the fundamental matrix. When the determinant is non-zero, that means the solutions that we have are linearly independent. But we knew they were linearly independent in the beginning because that's how we constructed the complementary solution. So because the Wronskian is non-zero and we have these linearly independent solutions, then our fundamental matrix is invertible. And we're going to leverage that piece of information in order to actually solve for a1 prime and a2 prime. So what we have here is the application of phi inverse to both sides of the equation. And of course, phi times phi inverse is just the identity matrix. And what that leaves us with is, that leaves us with a system where a1 prime and a2 prime are readily available. In order to solve this, what we'll do is we'll substitute in for the inverse of our fundamental matrix, and that's provided right here. And this is the standard for a 2 by 2 matrix where we have swapped the functions on the main diagonal, the elements on the main diagonal here, and then we've put a negative for the off-diagonal elements and divided by the determinant. And remember, the determinant is the Wronskian. So substituting that in and then multiplying by the vector 0 times f, we can see readily exactly what we're going to end up with here. a1 prime is equal to this first entry divided by the Wronskian, and that's what we have here. And a2 prime is equal to the bottom term divided by the Wronskian, and that's what we have here. So we've solved the system of equations for a1 prime and a2 prime. And now all that's left to do is find a1 and a2, which we do by direct integration. We can integrate. We notice that the right-hand side functions here are functions of x, and so we're just going to integrate with respect to x. And that's what we have down here, the integration of the derivatives in order to come up with what the a1 and a2 functions are. And so really the variation of parameters, what we've done is we've walked through a straightforward process in order to find these varying parameters. And it's easy for us to see that they are based upon whatever the external forcing is. Whatever the F is, that's going to tell us what the A1 and A2 parameters should be. Substituting back into our guess for the particular solution gives us this general form for the particular solution. And then of course, once we have the particular solution, all we have to do, we have our particular solution, is we're going to come in and construct our general solution. So this is the general solution created as the sum of the complementary solution plus the particular solution. There's one final note that I've included down here, which is, by the way, if we think about the complementary solution and its derivative, what we can see is we can see that the complementary solution appears as the top equation in this matrix setup, and then the derivative of that. So the y prime of the complementary solution is this second equation. Well, but what do we notice? We notice that this matrix is the fundamental matrix. It really is a fundamental piece of solving ordinary differential equations. We'll learn more about this when we look at systems of ODEs, but it's important to realize that the fundamental matrix comes up all the time. That's it. I just wanted to give you a little bit of background on where variation of parameters comes from, and once we see that it's just a simple assumption, which is a modification of the complementary solution, replacing the constants with functions, i.e. varying parameters, then all we do is plug it in, solve, and we can find what those two varying parameters are in order to come up with a particular solution. Thanks very much.